Alright, this is a video over shear, and moment diagrams. So let's say we have a force of 10 newtons, 10 newtons right here. What shearing is let's say this is glued right there. So maybe glue, that is glued right there. There's a force in the glue that's, this 10 newtons is forcing the glue to want to go that way, and the wall is wanting to hold it steady, so the wall must provide some counter force that's equal to this force. So this force is actually 10 newtons, so the wall must provide some counter force of 10 newtons. So inside the glue, there's a shear force of 10 newtons. And any part inside this block would have a shear force of 10 newtons. So the block has some internal resistance, just as the glue does, that provides a shearing resistance force. So if we were to increase the length of this, and we kept this at a force of 10 newtons, what would be the shearing force right here? What would be the shearing force right there? Well, before we go there, let's just find the shearing force right here. So pretending that this part doesn't move, what's the shearing force right here? Well, if there's 10 Newton force being applied here, that means this is applying some force downwards. So there must be some counter shearing force upwards of 10 newtons. So the shear force right here is 10 newtons. Now if we go here and pretend that this is stable, what's the shear force right here? And again, the answer is 10 newtons. And the same as here, 10 newtons here, 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 and here. So the shear force inside that glue is 10 newtons. And the shear force throughout this entire beam, from this point all the way over here, is 10 newtons. So anywhere you looked in here, if this could not resist a 10 newton shear force, the beam would slide past each other. So this would just slide down. Like if it couldn't, like maybe right here, this could not resist a shear force of 10 newtons, this part of the beam would just fall straight down, and this one would just stay static. Now you're probably thinking, like I would be, that, okay, the farther out a force is, now the farther out this force is, there's another force that we need to talk about, and that's the moment. Actually, it's going to be the bending moment. So remember, the shear anywhere in this beam is 10 newtons. However, the farther out this force is, the greater this is going to want to start rotating that way. So the moment increases the farther out this force is. And that's different from the shearing. Shearing is just whatever forces is keeping this from going down and this from going up. That's shearing. The bending moment is what's preventing it from going this way. So there must be some force that counters that makes it want to go this way. And they're actually related. So if we were to look at the shear and moment diagrams, so we'll say this is shear, and shear is usually written as a V. So we'll go straight down, and right here it goes up to 10 newtons. So there's a shear of 10 newtons, and it's constant all the way across until we hit another force, and the next force comes from the wall, so then that stops and we go straight back to 0. So the shearing in this beam is 10 newtons all the way across. What about the moment? And again, the moment is what's going to make this most likely going to break. What's going to cause this to want to just swing down that way? And usually moment is what causes something to break. It's not the shearing. Not shearing that causes something to break, but the moment. Because the shearing is the same throughout the beam, but again, the moment in the beam right here is relatively small. The moment here is relatively big, and it just keeps getting bigger and bigger and bigger until we're all the way right here. And we can calculate this moment relatively easy if we know this distance. So let's say this distance is 0.5 meters, and this is 1 meter, 1 meter. So we have 1, 2, 3, 4, 5, 5.5 meters, right? 1, 2, 3. So yes, so the moment right there would be 55 Newton meters. So that would be the moment right here. But what about the moment maybe right here? Well, if we just pretended that this didn't move or rotate at all, if we looked at the moment right there, this must have some internal resistance to moment. So let's find out what that internal resistance to moment is. So it must counter this 10 newtons. So that's 0.5, so that would be the moment for this point right here would be 1, 2, 3, 4, 5, 45 Newton meters. So if we kept on going, we'd see that this point has a moment of 35 Newton meters, this point 25, 15, and this right here would have a moment of 5 Newton meters. So if we were to graph the moment, what's the moment in the beam right here? Is there any moment in the beam? There's no moment until we get to this point. So the moment is 0 until we get right there. And the moment right at the point where this force is, that's 0. But as we go across, we get to 5 Newton meters right here, 15 Newton meters. Whoops, that's a little off. 15, 25, 35, 45, that's off a little, 45, and 50. So that's our moment. So it goes all the way up there. So we can actually look anywhere in this beam, we can just go straight down. We can see the shear, which would be right there, which is 10 newtons. And we can see the moment. And that moment would probably be 20 Newton meters. Now notice, if this length right here is 1, 2, 3, 4, 5, 5.5 meters. So if we multiplied 5.5 meters by 10 newtons, we got the 55 Newton meters, or the 55 Newton meters. Notice that's the same as the area under here. The area under here is 55 Newton meters, where you have a height of 10 newtons right here, a height of 10 newtons, and a width or length of 5.5 meters. So the moment is actually equal to the integral of the shear force over the length. So the area under this line represents the moment. Now if we were to say we instead added an additional force, let's say we added an additional force right here of 10 newtons. So right here, this would shoot up an additional 10 newtons, and that shear force would now be 20 newtons. 20 newtons at this point. It would go all the way until we hit the wall. All the way. What would happen to our moment? Well, that wouldn't affect any of the moment prior to the 10 newtons, but after it would. So now let's find the moment here, 35 Newton meters. So then we have to add the additional moment due to this 10 newtons. So we have 1 meter times the 10 newtons. So that's an additional 10 newtons. So that would be right there. Whoops. Right there. And then we'd have an additional, so right here, we still have the 45 Newton meters. Then we want to add in due to this 10 newtons being applied there, so that's 2 meters. So that would now be the moment right there would now be 65 Newton meters. So 65, we'll say maybe right there, and then finally all the way at the end, which is 3 meters away, that'd be the 55 plus the 30 newtons, so we'd have 85 Newton meters. And that might be right there. Oops. And again, notice that the area under this right here is equal to the 85 Newton meters. So it's all about the integration of the shear force over the distance.